So welcome you to this problem solving session. So last two problem solving sessions we solved some problems related to assignment number 4, which essentially deals with Bayes and min-max estimation. Now one common doubt many of you were having was about problem 2e, where you have to find a conjugate prior in the binomial n theta case where n is a parameter. So let us look at problem 2e of assignment number 4. So what you have is x as binomial n theta. What I assume is I have only single observation over here from the binomial. And n is a unknown thing, so that is a parameter. And theta belonging to 0, 1 is known. So that means parameter is the sample size n in the binomial case. So what is the f theta x? Is factorial n, factorial x, factorial n minus x. This is n choose x, theta to the power x, 1 minus theta to the power n minus x. If x is between 0, 1, 2, up to n. So I need to get distribution of n so that whatever distribution I assume, when I look at the posterior distribution, it belongs to the same family. So note that here 1 minus theta to the power n is coming. So somehow I should get something so that something to power n comes. And n is an integer value, positive integer values. N can take value 1 to so on. So Poisson distribution looks like a possible choice, but the only problem with Poisson distribution is it can take value 0 also. But here n is a sample size, so n takes value 1, 2 and so on. But that's not a problem. I can always truncate binomial distribution. So this suggests that I should consider my prior to be f s n. So prior of distribution s is the random variable at the point n. This is, let me put as c lambda e to the power minus lambda, lambda to the power n by factorial n for n is equal to 1 to so on, where lambda is a given positive constant. I can consider this to be prior. Now for this to be prior, this would be a proper probability distribution. That means c lambda of sum of this should be 1. So that means c lambda should be nothing but summation n is equal to 1 to infinity e to the power minus lambda, lambda to the power n by factorial n whole inverse, right? Because total sum has to be 1. That is what I have chosen c lambda to be this. So I can choose this to be, yeah. So how much is that? I know that total probability is 1. Summation n is equal to 0 to infinity of this quantity is 1. So this would be same as 1 minus n is equal to 0. N is equal to 0 is nothing but e to the power minus lambda, right, to the power minus 1. So that is what it is. Now if that is the case, then the posterior distribution in this case is, let me write down q of s given x, theta given x. This should be proportional to f theta x, that means joint PDF of theta and s, so f theta x, and then f s n. So there is no theta, so f s n given x. So that is same as f theta. This should not be f theta x because n is a parameter, so this would be f n x, right? Yeah, so this would be same as f n x and all that. So prior you can denote by different function g, so gsn. So this would be same as f n x and gsn, right, prior. And how much is that? So I just need to consider, because it is I am considering as a function of n and x is a constant, so I just need to consider only terms involving n. terms involving n in fn x is factorial n upon factorial n minus x. Then 1 minus theta to the power n minus x. Term involving n, factorial n minus x, 1 minus theta to the power n minus x. And then c lambda I did not bother because it doesn't involve n. E to the power minus lambda doesn't involve. So lambda to the power n by factorial n. In fact, here I can forget about 1 minus theta to the power minus x also, because that is also a constant. It does not depend on n. So this becomes lambda, so which is further proportional to lambda into 1 minus theta to power n. In fact, I can put n minus x, doesn't matter, because here I can put lambda to the power n minus x into lambda to the power x. And lambda to the power x gets involved into proportionality constant because lambda to the power x does not depend on n by factorial n minus x. And what is the range? X is fixed. So x is less than or equal to n. Right? So what you have is x is less than or equal to n. X is fixed. And n is an integer. X is also an integer. So that means n can go from x, x plus 1, and so on. So what is this quantity? So q of s given x, in fact, you know what exactly this is? This total sum is e to the power lambda 1 minus theta. So it becomes e to the power minus lambda 1 minus theta, lambda 1 minus theta to the power n minus x, factorial n minus x for n is equal to x, x plus 1, and so on. So which is again a truncated Poisson distribution. So we started with a truncated Poisson prior, and it was truncated at x equal to 1. When I do that, I again get a truncated posterior distribution with truncation at the point x. So this is also truncated Poisson. With truncation point at x. So that was one of the problems which many of you had asked. Let me do example 6, which we have done many times, but let me do it once more. So what you have is x1, x2, xn, IID normal theta sigma naught square, theta belonging to theta, which is r, sigma naught greater than 0 is known. Estimand is g theta is equal to theta. Loss function is square error loss function. So L theta A is same as A minus theta whole square. A in the xn space A, which is whole real line, and theta belonging to capital theta, which is again whole real line. Now prior is normal mu naught tau naught square. What does that mean? That means your f, let me write down that as g s theta. So the prior at the point theta is nothing but 1 by tau naught root 2 pi e to the power minus 1 by 2 tau naught square theta minus mu naught whole square. Theta between minus infinity to infinity. So it is a function of a theta. Mu naught is a given constant. Tau naught is also a given constant. Sorry, tau naught is positive because tau naught is standard deviation. Find the Bayes estimator. Right? So for so Bayes estimator delta pi x is nothing but, because it is a square error loss function, So it is a posterior mean. So to find the posterior mean, I need to get the posterior PDF. So posterior PDF is f of s given x, when s is fixed at theta and x is fixed at small x, which will be nothing but f theta x, that means joint distribution of x given theta, into density of marginal of theta, which is fs theta, which I am denoting by gs theta. And f theta x, I know x1, x2, xn are IID normal theta sigma naught square. So that is same as product I is equal to 1 to n, 1 by sigma naught root 2 pi e to power minus 1 by 2 sigma naught square xi minus theta whole square into gs theta, which is 1 by tau naught root 2 pi e to power minus 1 by 2 tau naught square theta minus mu naught whole square. So in the posterior distribution, I just need to collect the terms involving theta, because posterior distribution is a function of a theta and x is a constant, x is fixed. So that means all the terms involving x would get consumed into the constant, proportionality constant. So I say that this is proportional to sigma naught is constant, so it will be 1 upon sigma naught root 2 pi to power n. That gets absorbed into proportionality constant, let me say called as Cx. This will come, so it is e to power minus 1 by 2 sigma. So Cx, I put a proportionality constant, e to power minus 1 by 2 sigma naught square, summation I is equal to 1 to n, xi minus theta whole square. So I have to collect just only terms involving theta. This tau naught root 2 pi also get consumed in Cx. Then e to power, there is a theta over here, so e to power minus 1 by tau naught square what I do is a lot of things again would get involved into proportionality constant. I collect the terms of theta square. So it would be n theta square by this, and 1 theta square would come over here, minus 2 theta nx bar by this. I collect the terms of theta square, theta, and make it a perfect square. And then you can see this, everything reduces to e to power minus 1 by 2 n by sigma naught square plus 1 by tau naught square. So C1x, because a lot of terms involving x or other constant would come, which would get consumed in Cx, and the resulting constant, then I call it as C1x. And then theta minus nx bar by sigma naught square plus mu naught by tau naught square divided by n by sigma naught square plus 1 by tau naught square. Whole square. So this looks like this C1x, you know what constant it would be. It turns out to be normal because theta is a variable. So theta with mean as this, and variance is 1 upon this. So that means S given x equal to x is normal with mean as nx bar by sigma naught square plus mu naught by tau naught square upon n by sigma naught square 1 upon tau naught square. And what is the variance? Variance is 1 upon this, so 1 upon n upon sigma naught square plus 1 upon tau naught square. So what is the Bayes estimator? Under the square error loss function, Bayes estimator is nothing but the posterior mean. So it is nx bar by sigma naught square plus mu naught by tau naught square by n by sigma naught square plus 1 by tau naught square. So this turns out to be the Bayes estimator. Now, you have to show that x bar cannot be Bayes. So I know that expected value of x bar is same as theta. So it is unbiased. So to show that it cannot be Bayes respect to any proper prior, I just need to show that it cannot have a Bayes risk 0 for any proper prior. So r theta x bar, which is expected value of x bar minus theta whole square, turns out to be sigma naught square by n for every theta. Sigma naught is a fixed quantity. So what do you get? So that means r pi x bar, Bayes risk of x bar with respect to pi, it would be expected value with respect to any proper prior distribution. But prior distribution would be a function of theta. It is a constant, so it will be expected value of a constant. So it is sigma naught square by n, which is not equal to 0. And you did a result that if there is an unbiased estimator, and if that unbiased estimator is also the Bayes estimator with respect to square error loss function, then the Bayes risk has to be 0. Now here Bayes risk is not turning out to be 0, so this implies that x bar cannot be Bayes with respect to any proper prior. Now, there was another thing which we have to show, that generalized Bayes. With respect to uniform prior. Uniform prior means your density is pi theta is 1 for every theta belonging to R. Or in other words, your prior density gs theta is 1. Right? So these are prior. Certainly it is not a proper prior, because if you integrate it out, total integral turns out to be infinite. So what I have to minimize? I have to minimize psi of a, which is expected value of theta minus a whole square with respect to posterior distribution. So it is a minus theta whole square. And what is the posterior distribution? F theta x into gs theta. So I have to minimize this quantity. And what is that? That is nothing but minus infinity to infinity. A minus theta. What is f theta x? We have written down, it is some constant, so which is 1 upon sigma naught root 2 pi to power n e to power minus 1 by 2 sigma square summation I is equal to 1 to n xi minus theta whole square is sigma naught square. So any a which minimizes this would be the Bayes estimator or the generalized Bayes estimator. So let's try to see that. So this is some constant, so I take it outside. Anything which involves constant I can take outside. I subtract x bar and add x bar. So it becomes summation xi minus x bar whole square by sigma naught square that gets involved into this cx, or let me call a new constant dx. Then 2 times summation xi minus x bar into x bar minus theta. Summation xi minus x bar is 0, so that goes away. So it becomes e to power minus n by 2 sigma naught square x bar minus theta whole square, that means theta minus x bar whole square. Dx goes outside the integral because this whole integral is respect to theta, which is dx times minus infinity to infinity a minus theta whole square d theta. So it is a square times this one minus 2 theta a times this thing plus theta square. So I put double derivative would be greater than 0 because a square term is coming with this integral. So it would be double derivative would be 2 times this integral. Integral is of an exponential, so it would be positive. So that means the minimum would be where derivative is 0. So where derivative is 0? So that means 2 times a minus theta is equal to 0. So that means a would be nothing but minus infinity to infinity theta e to the power minus n by 2 sigma naught square theta minus x bar whole square d theta divided by 2a. So just this quantity. So minus infinity to infinity e to the power minus n by 2 sigma naught square theta minus x bar whole square d theta. Now you know that this is same as sigma naught by root 2 pi. When you put at sigma naught by root 2 pi, this becomes a proper density. So it becomes density of a theta with mean as x bar and becomes a mean. So this turns out to be x bar. So it turns out to be generalized base. Now let me go quickly to problem number 10, which deals with similar kind of a thing, because I can use the same. Let me write down this problem number 10. So let's see what problem number 10 says. Problem number 10, I do only one part of it because the minimexity I have not covered, so I'll not do the minimexity part of it. So what it says is x1, x2, xn IID normal mu sigma square, where mu and sigma both are unknown. Let me call this as theta. Your estimand g theta is mu, and you are considering square loss function, so that means L theta mu is nothing but a minus mu whole square, theta belonging to capital theta, a belonging to a, which is whole r. What you have to show that for any estimator delta, supremum risk is infinite. So let me just use, can I use this fact? Yeah, I can use this part. So my claim is for any estimator delta, supremum over whole theta r delta theta is infinite. That is what you have to show. Now to show that, what I do is I first fix sigma square so that sigma square is known. So fix sigma greater than 0. You can consider this to be known. Now if sigma is known, I consider the prior, which I considered same as in the last case, prior for mu. I consider normal mu naught and tau naught square. Then I know that posterior distribution of is nothing but normal nx bar by sigma square, because here I am in place of sigma square, you have a sigma naught square, you have a sigma square, which I have taken to be fixed or known, plus mu naught by tau naught square by n by sigma square plus 1 by tau naught square and 1 upon n by sigma square plus 1 by tau naught square. That is what the posterior distribution we obtained. Now I consider first take I supremum only with respect to mu. So I consider supremum over mu of any estimator r delta mu sigma. So sigma is fixed. I just take supremum over mu belonging to R. I know that maximum risk is always greater than or equal to average risk. So this would always be greater than or equal to average risk of delta with respect to the prior distribution pi. So this is same as R pi delta. So supremum risk of delta is greater than or equal to average risk of delta. But delta is any estimator, so average risk of delta would be bigger than or equal to average risk of Bayes estimator, because Bayes estimator minimizes the average risk. So this would always be greater than or equal to Bayes risk of Bayes estimator. So I need to find out what is the Bayes risk of a Bayes estimator. Bayes estimator is given to be this. So R pi delta pi is total risk, so which is same as expected value of S into expected value of S given X, right? This was the usual risk, classical, and then you average with respect to the prior distribution of theta. And then estimator is nothing but nx bar by sigma square plus 1 by tau naught square divided by n by sigma square plus 1 by tau naught square minus theta. Theta has been replaced by a random variable s whole square. All right? Now note that this is E of S and then E of X given S, right? So this is E of X given S and S. It is kind of expectation with respect to joint distribution of X and S. The expectation of joint distribution of X and S can be written as expectation of X into expected value of S given X. So this is same as E of X into E of S given S. S given X is kind of a posterior distribution of same thing, because it is a square, so I can write down this as S minus all that. Now in the posterior distribution, this is the mean. Bayes estimator is nothing but mean. So it is a mean of S in the posterior distribution. So that means if you look at this quantity, it is nothing but the posterior variance of S, because Bayes estimator is nothing but mean. So S minus mean whole square, so it becomes variance of S given X. So it is same as posterior variance of S. And what is that? Because posterior distribution I have obtained as normal with mean as this and variance as this quantity. So it is same as 1 upon n by sigma naught square plus 1 by tau naught square. This is constant. It is not depending on x, so this expectation would be same as this constant 1 by n by sigma naught square plus 1 by tau naught square. So whatever may be the prior distribution, your supremum over mu r mu delta r mu delta, or I have written down r delta mu sigma is always greater than or equal to, we have seen, is r pi delta pi, which is same as 1 upon n by sigma naught square plus 1 upon tau naught square. Now prior is in my hand. Left hand side does not depend on prior. So left hand side does not depend on tau naught. So it says that supremum of this risk is always greater than or equal to this for every tau naught greater than 0. This would be sigma square, sorry. So if it is greater than, for every tau naught greater than 0, I can take tau naught going to infinity, in which case it becomes 0. So that means what you get is, so supremum over mu r mu belonging to r delta mu sigma is always greater than or equal to sigma square by n. So that means when I look at supremum over, now I keep on varying mu and sigma both. So I keep on varying now sigma also. R delta mu sigma will always be greater than or equal to supremum over sigma greater than 0 of sigma square by n, which is same as infinite. Because supremum of sigma square by n is infinite. So supremum of an estimator delta is greater than or equal to infinite. That means it is infinite. So it means supremum over theta belonging to capital theta of R delta theta is infinite. So that means if your loss function is square error, the supremum risk of any estimator is infinite. So the minimexity is not a good criteria, that means over here, because for all the estimators, maximum risk is infinite. So minimizing that doesn't make any sense. So let me stop here for this module. In the next module, we'll do some more problems on Bayes and minimax estimation, which are there in assignment number 4. So thank you very much.